All right, hey everybody. So today we're going to be talking about physical and chemical changes. So before we get into that, let's review some of the terms that we talked about with the physical and chemical properties. So corrosive. Corrosive basically means it can eat away at something, like an acid eating away at clothing or skin or a table or something. Flammable means it can catch on fire easily. Accurately means it is the correct value. Qualitative means it's a type of physical property, and it is basically things that do not change depending on how much you have. Whereas quantitative is another physical property, but it does depend on how much you have, like the mass or the length. All right, so let's talk physical and chemical changes. So physical changes are things that can change the substance without changing the chemical composition. So I can change what it looks like, I can change how much there is, but I'm not changing what it is. So let's say that I have a soda, okay? So I have a Diet Dr. Pepper, generic. Let's say that I drink the soda, okay? There's less soda now in the can than there was, but it's still the same soda. Okay? That would be a physical change. If I have a piece of paper and I tear it up, that is another physical change. It is still paper, but it is now two separate pieces of paper. So things like cutting paper, melting ice, boiling water, breaking glass, it's all the same stuff. It's just you're changing the shape, maybe what it looks like, something like that. Maybe you're changing the volume of it. Chemical changes, on the other hand, you actually have to change the chemical composition of a substance. This is also known as a chemical reaction. So this is where you are actually changing the compound or molecule. So rusting, burning, rotting, exploding, those are all examples of things that you're actually changing the molecules or compounds. They are no longer the same as what they once were. You actually change the substance. So physical changes are easily reversible. Well, most of the time. I mean, if you tear apart some paper, you can tape it back together, but it won't really go back. You don't get any new products. It's usually just a state change, like ice melting. It's still water. It's just in a different form. Chemical changes, on the other hand, are not easily reversed. Usually we get new products being formed, reactants being used up. Think of chemical changes like cooking. You put in ingredients, you get out a product that looks totally different from what you put into the oven. Chemical changes often result in heat, light, sound, or fizzing, like bubbling. Not boiling, bubbling, but like when you open up a soda. Or if you put Alka-Seltzer into a cup with water. You could get electricity being produced. Maybe a precipitate forms. Precipitates are solids that occur when you mix two liquids together. Those are chemical changes. Wood burning is an example of a chemical change. So I can't get those logs back. Once they're burned, they're gone. You can't turn ash back into wood. It produces a lot of heat, a lot of light. You can hear the crackling. You could probably harness some of that heat to create electricity if you wanted to. So let's look at the difference between physical or chemical. Is it properties or changes? Oop, never mind. Okay, so let's look at some signs that a chemical change has occurred. So physical changes, the object remains, but might be a little bit different. It might be melted, might be broken in half, something like that. Like snapping a pencil in two, melting some butter for some tasty popcorn. Maybe if you have a cup of ice and you let it sit out for a little bit, it melts into water. Or if you put some slightly melted ice cream into the freezer and it hardens over time as it freezes. Those are physical changes. Chemical changes, on the other hand, the object has new properties. So if you're burning that log and it turns into ash, ash has very different chemical properties than that wooden log. If you're cooking something, so let's say that you are mixing up some cake batter to make a delicious cake. Does that batter look anything like the cake after it comes out of the oven? No, they look very different from each other. They have very different properties. What about an egg? So let's say that you eat eggs in the morning. Does the yolk that comes out of the egg look anything like the scrambled eggs once they're done? Probably not, unless you undercooked them. Alright, so some signs that a chemical change has occurred might be a gas being produced, formation of a precipitate. Again, a precipitate is when you get a solid forming from two liquids that are mixed together. Maybe bubbling or fizzing, sound or light being produced, or a rapid temperature change. If you mix two things together and all of a sudden the temperature shoots up or down, that is probably a sign of a chemical change. Now, I'm not talking about if you put a beaker on a hot plate and it starts boiling. That is expected. This is something that is totally unexpected. It shouldn't happen, but it does. That's a chemical change. Or if you have an unexpected color change. An example of this would be if you have two solutions. One of them is white and the other one is pink, or the other one was red. So if you mix something white and something red, what color would you expect? Pink. If you mix white and red and you get blue, that's probably a chemical change. Okay, so if it's expected, that's one thing. That would be physical. Okay, so if you're just mixing white and red and you get pink, that's physical. If you mix white and red and you get something crazy like blue, that's way unexpected, that would be chemical. All right, while we are talking about physical and chemical changes, let's talk about the law of conservation of mass. So the law of conservation of mass states that although a reaction may have occurred, the amount of mass always stays the same. Okay, so if I start out with 10 kilograms, I better end up with 10 kilograms. Okay, it's just transferred. So it doesn't magically appear, it doesn't magically disappear. It's always there somewhere. Now, it may have escaped as a gas, you may not have captured it, but it's there somewhere. So atoms are recycled. They can't be created, they can't be destroyed. All right, so in this picture right here, I see that I have a light bulb, same mass as the weight. You can tell they're the same mass because they are equal in the scales. After the reaction, yeah, the light bulb turned on, but it's still got the same mass as the weight, okay? The mass did not change. It is the same. Let's look at how we would see this in chemical format. So let's say I have 16 grams of methane mixed with 64 grams of oxygen. What's the total mass of my reactants or ingredients here? So if you add up 16 plus 64, that equals a total of 80. So if I have 80 to start, I better end up with 80. All right, so I end up with 44 grams of carbon dioxide plus 36 grams of water. Add those two up, 44 plus 36 is equal to 80. They are equal to each other. So the law of conservation of mass basically says that everything must equal each other. So this example says if I have 18.02 grams of water to start and I break it down into hydrogen and oxygen, how much hydrogen am I going to be left with if I get 16 grams of oxygen? Okay, so this is just subtraction. You would do 18.02 minus your product, which is 16.00. That means that what's left, your hydrogen, must be 2.02 grams. Okay, so whatever you have on the left has to equal the total of what you have on the right. Now, I told y'all I love Harry Potter, and I love incorporating pop culture and movies into chemistry. So this is a clip from Harry Potter and the Sorcerer's Stone, or Harry Potter and the Philosopher's Stone if you do the British version. But anyway, this is a scene where Professor McGonagall transfigures herself from a cat to her human form. So if you're not familiar with the series, she is an animagus, which means that she can basically convert herself from between humans and an animal form. So she can go back and forth between a human form and a cat form. So we're going to look at a clip showing her going back and forth. Alright, so this is conservation of mass, Harry Potter style. Hopefully. There we go. Okay. So that's Hogwarts in the background. So what is wrong in this picture? So again, conservation of mass says that mass cannot be created or destroyed. It just changes form from one to the other. So they're late to class. There's McGonagall being all sneaky.
Amazing.
Doing a very bad job of sneaking into class.
We're gonna go space if we were late.
And busted. So what exactly is wrong with that picture in terms of conservation of mass? So the approximate mass of that cat was maybe...
That was bloody brilliant.
Not that much.
That assessment, Mr. Weasley.
Okay.
Perhaps it would be more...
Alright. So skipping ahead. Okay. So Maggie Smith, who plays Professor McGonagall, is about 115 pounds. That cat is maybe 11 pounds. Okay, that cat is like way smaller than McGonagall.
Amazing.
Okay, so how do you go from 11 pounds to about 115 pounds? You don't. Okay, even in the metric system, that is a crazy difference. So yes, Harry Potter is just fantasy. Very cool to watch, but it does not follow the rules of chemistry and the law of conservation of mass. Alright, so that's where we're going to wrap for right now. So today we covered about physical and chemical changes. Physical changes being where you just change what it looks like or how much you have, but you're not changing what it is. Chemical changes actually change the chemical structure of the molecular compound. And then the law of conservation of mass says that whatever you start out with, you have to end with that same amount. The atoms get shuffled around, but overall you have the same atoms there, period, beginning to end. They don't appear, they don't disappear, it's not magic. You can't go from an 11-pound cat to a 115-pound actress. It just doesn't happen. So we have to follow the chemistry laws if we want to stay within the guidelines.